This video is called Polarity because our third goal for this review unit is to rank molecules out according to their polarity. This is one of the most important things we need to do all semester, so I want to make sure we're really comfortable with it. I'm going to show you this figure. It's not from your notes, but I want to start really bridging from the last unit when we talked about the idea of the hydrophobic effect. The hydrophobic effect, we said, was the clustering of nonpolar molecules away from water, minimizing the surface area of contact with water. Let's imagine that we have a beaker full of water, and we have these kind of tan brown molecules, and that they're very nonpolar. Obviously, they're just schematic here. The dark blue halo around each of these is the area that is interacting with water. And because that's not a very productive interaction between polar water and nonpolar molecules, that's not a very satisfying energetic situation for these, either the water or the molecules. Now, if these tend to bump into each other and cluster, which they will do just because they're floating around, you're going to have areas where the nonpolar area is interacting with itself rather than water. And the more they bump into each other, the less surface area of interaction with water you have, and the more surface area you have of the interaction between the nonpolar molecules. Note, this is not happening because there's a strong interaction between these nonpolar molecules. It's actually a very weak interaction. It's happening instead because we are making less surface area of contact between nonpolar and polar molecules. Okay, so let's move on to our actual notes here. The next page, we have some terminology that I want to go over. Again, most of this is review, so bear with me if this is something that is obvious to you. When we want to identify polar molecules, we're interested in those that we consider to be hydrophilic or water-loving, and those tend to be water-soluble because they have a positive interaction through hydrogen bonding with water. Molecules that have a lot of nonpolar bonds are going to be hydrophobic or water-fearing, and they are water insoluble to some degree, meaning they will not disperse in water. We have a new term that you may not be familiar with here. Things that are hydrophobic, that is water-fearing, are lipophilic. Lipid means nonpolar molecules, and lipophilic means therefore molecules that are loving lipid in nonpolar environments. We're going to use this later to describe certain types of vitamins. We have some that are water loving, and we have some that are lipid loving or lipophilic vitamins. So that's this terminology that we're interested in, and I want to emphasize to you that on the one hand, it's fairly straightforward to consider things that are polar and nonpolar into two camps. I'm going to back up to a previous page, and I want to show you that previous page on 3. Let's take two example molecules here and point out that hexane here on the left is very nonpolar. It only has CC and CH bonds. So that's very easy to identify as something that cannot interact with water. Glucose over here, which also has 6 carbons, has a lot of CCs and CHs. On the other hand, we consider to be a polar molecule because it has very polar bonds like CO and OH. So it's very straightforward skill to learn how to do, and we'll practice this. It's easy to learn to put these into two camps. Let's take a moment here while we've got these molecules out and have you practice something else. I'd like you to, on one of these molecules, either the hexane on the left or the glucose on the right, I would like you to draw a water molecule appropriately interacting with one of these molecules, and I want you to draw the water acting as a hydrogen bond acceptor. Pause it for a moment. Draw a water as a hydrogen bond acceptor with a true hydrogen bond somewhere on these two molecules, and then start her up again. Okay, there's a lot of places you could put this, but only a few where you can do it right. So I'm going to just draw one out and show you how it would possibly work. Here's a water molecule, and we can draw it there. I can circle 3 atoms, and that's 2 oxygens, which are electronegative, and there's a 1 H being shared asymmetrically between them. This is the acceptor on the water because it has a pair of electrons, and this is the donor on the glucose alcohol because it has the hydrogen covalently attached to it. If you drew something like this, that's a perfectly good hydrogen bond. However, it's not quite correct for what I asked because in this case, the water is the donor and the oxygen on the glucose is the acceptor. If you did something like this and tried to make this into a hydrogen bond, we would say no, can't be a hydrogen bond because the CH right here is not an electronegative contribution there. The carbon is not electronegative. So that's a good practice for us. Let's turn back to something a little more sophisticated. Back to where we were on the previous page. We're going to leave this part, the last part of the chart here, for the next video. I want to finish off with one more exercise, something a little more subtle. Because it's one thing to put molecules into 2 camps, polar versus nonpolar. That's a fairly straightforward skill. But what we're really interested in is a spectrum of polarity, from fully polar to fully nonpolar and everything in between. It's much more important to rank polarity of molecules that are even fairly similar to each other. Okay, I'd like you to take a look at these 3 molecules, which are molecules we'll learn about in this class, and I'd like you to rank their polarity. Stop the video, put a 1 next to the molecule that is the most polar, and then a 2 and 3, 3 being the least polar. Okay, I hope you took a moment to do that. I want to point out that these molecules are very similar. I also want to point out that they're all very polar. However, they have subtle differences in polarity that we need to rank out. And I'd like to point out that we can do so by looking at what's different about these molecules. Everything is the same in these molecules except these portions right here. Now, if we look over on the right here, we're going to see something that is all CC's and CH's. That means this is going to be the least polar, and that's because that portion of the molecule has only nonpolar parts of it. The other 2 are both polar. If you look on the left and in the middle, they're both polar. Did you guess which is the correct answer, though? This in the middle is the most polar, and this on the left is the middle one. These are so similar to each other. It's just 1 hydrogen difference. So what's the difference here? Well, it's a simple thing that we can write down, and it's important for this class. And if you don't know it, let's get it out of the way here. Full charge is more polar than neutral. So that full negative charge that we get when we deprotonate that carboxylic acid, that's going to be more polar and therefore more water soluble than the same functional group with a proton on it that's neutral. Okay, let's stop there.